Hello, everyone, and thank you so much for coming. Today we have our first speaker, Jihoon Kim from Cornell University, working with Professor Gennady Shvets. And today he'll be talking about laser shaping using stimulated Brillouin scattering for inertial fusion energy. And we'll take a bunch of questions at the end, but if you feel like you're going to forget your question, feel free to just put it in the chat. And with that, Jihoon, feel free to take the floor.
Yeah, so hi, nice to meet you, everyone. Kavita gave the introduction, so I'll just try to make it more general because I know there's a lot of different people. So first part, I'll try to give an overview of inertial fusion energy. Well, I think a lot of you knew this, but I actually am not from a nuclear fusion background, so I had to study this. So I think it would be nice to have a kind of overarching background and try to present where I stand in this problem. And then I'll try to move into a little bit of more specifics. I try to keep a lot of, it's not like hard math, but it's tedious math. So I kept most of them under the rug and try to just show what I think, like the physical pictures I found. So everyone knows this, guy. He invented E equals delta MC squared. I don't think there's a lot of room to make typos, but yeah. Anyway, so that's kind of how this whole fusion is interesting. So you try to combine two nuclei into one different nuclei and a neutron, and then there's a little mass difference, and the charged particle will have different energy, or the non-charged neutrons will also have some energy. If you can somehow capture the energies of these particles, and that's how you get energy from nuclear fusion. This is the most popular one, but I also know in our rise up, there are people who work with PB fusion. So this one is proton boron, and the products are free charged particle. I think the key difference between these two are this one has neutrons, which is always a pain in the butt to capture because they're not charged. But in case of PB fusion, all of these are just helium, so it's not really radioactive, and that's why a lot of people are working on it. There are some problems that I think some people know how to solve. I'll not go into too much detail. But today in this talk, I'll just talk about DT fusion because this is what a lot of people are working, and this is in some sense the easiest nuclear fusion to make. So fusion and fission are very nice. If you think about the kind of energy to mass conversion ratio, gravity or like the waterfall old school generator you see, 1 kilojoule per kilogram. So that seems like a lot of energy until you go to chemical, which is I guess the one where uh, the weird cone-shaped building where you burn stuff. That's 10 megajoule per kilogram. And then fission suddenly he's 10 to the 14th. And this is very nice, so that's why they had a lot of fission plants, but then, a lot of meltdowns have happened. So people are saying, okay, maybe we don't like uranium that much. Maybe let's move to fusion, which has the um, same kind of kilogram to joule efficiency, but also is kind of very hard to run into a kind of runaway explosion. So examples of fusion, the most common one are the stellar core. You just see the sun every day, and if you look into it directly, you'll get blinded. So that's kind of telling you how much energy this produces. But on Earth, we have tokamaks and stellarators. This is, I think, another prong of the fusion energy that people are working on, maybe not the rise-of itself, but our rise-of mostly concerns itself with inertial confinement fusion. So, uh, so fusion seems like a very good idea, but why haven't people done this so far? It's basically because the two kind of ingredients for fusion is DT, which are both charged particles. So if you want the deuterium and tritium to really become close to each other, you have to overcome the Coulomb barrier. And you need to make the two nuclei go very close in the order of femtometers, or the kinetic energy of these particles need to be in the order of MeV. So you just don't typically see maybe you can accelerate them in an accelerator and try to collide them, but it's a one-time event. You want a thermal bath of deuterium and tritium or other kind of fusible elements, like thermal population, a large quantity of them to make fusion energy. So a lot of what's very nice is you don't actually need to heat them all the way to MEV temperature. If you have studied Boltzmann distribution, then you see that there's a kind of characteristic. If you have a K order of KV temperature, then there's a little tail here. And if you can put enough of these fusion constituents into this tail, then they can actually overcome the Coulomb barrier and then create a self-heating burn, which will which will generate a self-sustaining burn. So sounds all very nice, but if you think about it, even KEB temperatures in the order of 10 to the 7 Kelvin is very, very hot. So if you try to keep this kind of very hot matter in a small volume, then it's not very easy. So one way to do it is gravitational confinement. You've seen this before. Use gravity, very, very high density, and very long time, billions and billions of years, and it naturally occurs. But it's bigger than Earth, and you don't want to live on sun. It's very uninhabitable. We can't build this. So what people came up with I never get the dates right, but back in the days, Soviet Union invented tokamak, and I think US invented stellarator. You use the magnetic field to kind of contain these plasma because you've maybe heard of magnetic bottles. And this is lower density, more like gas-like, and longer time, minutes and hours of burning plasma. Um, do I want to say anything interesting? So I think this is more like a kind of slow burning of fusion fuels. And then you have inertial confinement where you compress and burn a small but very dense pellet of DT fuel. And you need to kind of compress them to very, very high densities, not many times, 1,000 times the solid's density. And then you need to make that happen in the order of nanosecond. And then unlike this magnetic confinement, you have to kind of blast the DT fusion pellet several times per second. So I think this was akin to like a car engine, which kind of undergoes several explosions per second. And I think this is like a more like a boiler burning type of thing. Two different approaches. I think both have its merits and disadvantages. And then there's more. So these two have been very um, like two leading schemes. And then there's our rise of colleague Marvel Fusion. They do something called micro accelerator based scheme. I don't know too much about it, but they have an archive paper, so you guys can take a look. Or there's some other companies which are not even from our hub, but Zap Energy tries to use pinch power to do some advanced configuration. So there's a lot of room temperature fuel in Marvel Fusion, or I think they claim no compression, if I'm correct, some kind of advanced geometry. But basically fusions, there are a lot of approaches and it's not a completely solved problem, which is why I think so many people are working on it and there's still some room for improvement. So among all these, I'll talk about inertial confinement fusion because that's what our hub is about. So how does inertial confinement fusion work? You have a hollow shell of DT, which you'll drive from the edges with, and then ablate the surface of these DT. So when there's ablation, then as a action reaction, there's a kind of rocket force that drives these shells inward. And as a result, they will form a hot spot surrounded by a cold compressed fuel and a low density corona. And then if this gets heated enough, then it'll cause a self-sustaining burn and explosion. So the requirements, so you can't just do this anytime, you need to reach certain conditions. So typically the requirements are like, you need to hit a temperature of around 10 keV, and you need to make the areal density of this to be 1.5 grams per centimeter. So typically the compressed fuels have a dimension of about tens of microns. So you need to make the compressed fuel density go up to like 1,000 or 300 grams per cubic centimeter. So hundreds or thousands times like normal desk density. So just the schematic, this is like a little cross section. So imagine you cut it here, there's a gas and there's a shell, and laser or some kind of driver would do a PDB work to simultaneously heat and compress the target to cause this burn and explosion. So how do we do this? It turns out that this is, in order to do this compression heating very efficiently, you can't just have like a flat top laser. You need something special. So these are some examples from nature physics. I'm not a target designing person, but at least even I know that you need to have different components, toe, foot, and then shock. The design people have come up with all kinds of very fascinating ideas. I think if somebody from the design area comes, then they can maybe talk about these. But basically, you need to compress a long or potentially long laser to the right duration, and it needs to be very intense. So terawatts, temporally shaped, and nanosecond lasers. Another thing I kind of learned while researching or trying to see why people always use 0.35 micron was at some point in the 70s, so people have been working on this for a very long time. They use a 1 micron laser and it caused horrible, like very bad laser plasma interaction. So instead of having a shell driving a gas and doing PDB work, you're trying to compress the balloon and then the balloon will blast, right? So if you drive these shells with the 1 micron laser, that's basically what happens. So um, a lot of old people in the fusion community say that the long wavelength really almost killed the fusion program. And then people learned that now people operate with 0.35 micron or kind of shorter wavelength so that the um, laser can uh, laser can push a denser mass such that the collision between these matter can alleviate a lot of these plasma instabilities. The take-home message of this part is you must use a very short wavelength light to avoid a lot of the plasma instabilities that plasma people know and love and hate. So I think everyone in working here probably knows about NIF. It was a really amazing scientific milestone. I think it almost there were like if I don't know how to do justice to this, but if you look at the literature, people try to do this since the 60s and 70s, and there have been so much development in the laser system, whole round design. So it's a really amazing scientific milestone, but this is still not a fusion power plant. So this is a one shot per day kind of deal, and each of these capsules cost not quite million, but 100K per target, and it takes like 6 months to design. This was in a sense, NIF was never designed to be a energy producing plant. It was a scientific milestone. Even that was actually really, really hard. But if you want a real power plant, then you need a target factory to produce many very low cost targets. So like if you have 5 shots per second, then that's 18,000 capsules per day per plant. And then you need a driver which is very efficient. So this the main reason for NIF being able to shoot once per day is it takes them entire day to, I think, charge up the flash lamps that drive this. But if you want to do this at a 5 hertz, then you need to shoot laser 5 times per second. So we don't obviously have a driver. And then something a lot of the people also forget is you need to collect the energy from the neutrons and then somehow convert that to energy in a steam plant, and then put a fraction of that to kind of self-sustain this a fusion power plant. And then if you look at this is a little bit outdated design, and I don't think the ignition yield was 46 megajoule. I think it's more like 5 megajoule. So you start with the 400 megajoule of capacitors, and you make a laser, and you get 1% efficiency, 4 megajoule. And then you have to frequency triple it because 1 micron will destroy the target. So then you have 0.5%, and then you convert that to X-rays, so you get 1.3 megajoule, and then you get 5 megajoule. So we lost actually 300 times the energy. And if we just want to recover the capacitor energy, we will need 300 times gain. And I'm a theory person, so theory person always likes to extrapolate their numbers. So this is a kind of theory scaling of how high the gain is. And even theoretical papers don't cite 300 times gain. People usually go say 100 and then they stop over there because everything is a little bit fantastic. So, and this probably needs 1,000 times gain to make this a working power plant. So there's certainly some rooms to improve. One, this is a really bad, well, flash lamps are bread and butter, but you probably don't want this for energy production. And we should probably skip laser frequency tripling because we lost more than 50% here. And then we also lost like 60% here. So that kind of sets the stage to why we're trying to use excimer lasers. There are actually other methods to kind of make drivers. I think Livermore's working on some, and like people have all kinds of ideas actually. But in this particular design from 2015 paper, this is an electron beam pumped KrF laser. So there is a gas of chromium fluoride and maybe argon as a buffer, and then you heat them using a pulse power electron yeah, electrons accelerate by a pulse power machine. And then when they're at an excited state and then they lose energy, they emit photons, which is deep UV laser light. So electron beams to gas and then the gas to the photon energy. And if you look at the efficiencies, it's really great. It's not like 1%. Pulse power efficiency is 90%. Electron beam transport from vacuum to this gas cell is 80%. And then I actually don't remember this part, but then KrF intrinsic efficiency is 12%. So if you compound all these, it's still 8% of efficiency. And there might be more physics involved as I think um, yeah, because some other groups in our Rise Hub is working on this. But even just looking at numbers, this excimer lasers are 16 times more efficient. Um, so if is everything solved, then I can just go home? Not really, because like all other technologies, this hasn't. You need to do something to make it a fusion compatible laser. So I stole this little snippet from Excimer. I hope they don't sue me for this because it's actually a company, but it has a short upper state lifetime and it has a low saturation influence, which basically means this whole fancy scheme can only produce very long, low intensity lasers or relatively low intensity lasers. The output pump is a flat profile continuous laser, which is weak and low. So we need to somehow turn that into powerful pulses. So another thing, I hope they really don't sue me. So you have a neutral gas and you have a seed beam counterpropagating a pump beam. And via this process known as stimulated Brillouin scattering, which I'll explain in the next slide, the pump beam can transfer energy to the amplifying seed. And also, as I found out, or maybe some other people also found this out, but can also, so it can do the job of transferring energy to amplify and also shape the pulse. So just for people who don't know what stimulated Brillouin scattering is, like me, like a few months ago. So you have a counter-propagating pump and a signal, and people learned about beat wave in their at some point in their undergrad. So these kind of counter-propagating two electromagnetic waves will cause an intensity grading by beat wave, and then due to electrorestriction, there will be a material density modulation which then becomes a refractive index modulation. Then that lets the energy transfer from the pump to signal possible. So, well, this is actually not that complicated, but this is just the equation. How the pump loses energy, well, no. This is how the pump couples to this refractive index modulation. This one is how the signal couples to the refractive index modulation. And then this is how the refractive index modulation is related to the pump and signal intensity. And then, like all theorists, I like normalizing. So this looks much better, but this is just the same equations. So seed, the physical picture is seed, the red term, is the counter-propagating pump, A, mediated by this acoustic wave. So when I was researching this, one thing that was very interesting to me was this problem was actually, at least this problem was completely, at least analytically solved by mathematicians in the, let me see, 70s. So this was a biological problem in the beginning. Exact solution of a certain semi-linear system of partial differential equations relate to a migrating predation problem. So you can think of this as a shark population and a macro population. Counterpropagating, the shark grows and macro dies. So shark is the kind of, you can think of shark as the seed pump and the macro as the pump. And then, yeah, there's a bunch of ways, like there's a lot of papers. So this was my first couple of weeks and trying to look at this. So you can think of a pulse of, well, Stokes front. So this is where the shark is sitting, and then this is time. You can see a pulse of shark eating a pulse of macros and growing. Or you can have a pulse of shark eating an infinite stream of macros. So this is very good and very bad in some sense, right? Because it is a completely analytically kind of finished problem. So can we just say we're done and just be done with the day? The exact solutions to these like anything more complicated becomes very involved. And I don't know how to read this. So this is an example solution of nth order super Gaussian sharks. This, but I mean, I derived it. I can probably write it. I can make plots, but I don't know how to understand this. It's kind of, typical mathematician analytical solution, not very useful if it becomes too complicated. So another approach that I tried to do was to make some simplifications. So I think I kept most of the normalizations and dropped some terms to get a very similar but slightly different equations and the co-moving variable and propagation distance. So signal propagation, pump depletion, overdamped acoustic wave. So we are sitting at the seed frame, which is which is the red one, and looking at a constant amplitude pump coming from this side. And then we kind of integrate over time to see what happens to the seed. So the front of the seed will always see a Fisher pump, and then it'll grow faster and also kind of move superluminally to the left. But it's not really superluminous, it's just that different parts of the seed have different growth rates, and as a result, the peak is moving to the left, but there's no real information transfer. So this is an example of Gaussian seed eating a constant pump. And you can recognize that the seed, the red thing, is completely depleting the pulse and then forms a steep front, which moves superluminally. And then this is a relatively simple system. So if you assume total depletion of pumped by the seed, then you get some conservation loss. Basically just saying that if the pump photon is completely eaten by the seed, then the photons are completely converted into the seed photon. It's just like Gennady said this is Manley-Rho, some old physicist name, but yeah, somebody found this in different contexts, I think. So so I did some numerical calculations to see what the Gaussian does, and Kavita at some point commented that I made triangular shapes. So this is exactly the triangular shape she saw before and that this is a different seed profiles at different times and different pump profiles at different times. Same color correspond to same time. You can see that the growing, before I go to that, so we have a numerical solution, and whenever I have numerical solution, and if I have an analytical solution, I always check them. So this is the mathematical kind of formulae for the sharks and macros analytic solution. So they are actually in quite good agreement. I think 7.6 and 3.2, the position is almost the same. So at least I know my code is not doing something horribly wrong. And then if you start with different kind of initial seed shapes, fourth order super Gaussian or eighth order super Gaussian, you can see the peak kind of grows like a polynomial. Results do yield almost the same result. And front of the seed pole steepens over time. And this kind of steepening holds for different kind of nth order Gaussian, but the peak growth, so this one is triangular, but this one looks like maybe a cubic. This one looks like a seventh order polynomial, maybe. So the growth and expansion or pulse evolution happens at a different rate. And the seed pulse's sharp edge kind of contains all the action. So just like this is for a physical picture. So um, because this seed is usually extremely sharp, you can almost say we had a conservation law, if you remember. The energy in per unit time is proportional to A naught squared. And then if there's a little motion of this peak to the left, delta t zeta peak, then you can almost say that the motion of the front peak times the peak intensity here is equal to the photon number. So by the same logic, if you know how fast the velocity this is moving, we know how much energy it should consume, so then we should know the peak amplitude at any given time. So kind of like going a little bit back and trying to describe the different pulse structure. Um, So at the very front of the pulse, pump depletion is very negligible. So we usually call this a linear regime, and everything is very well defined here. Something crazy happens in all the kind of pump depletion and seed growth happens here. So we call this a nonlinear region. And then there's no pump behind, so we call this, well, nothing happens. So I just called it nothing. So we just described the nonlinear part growth, and we just said the peak motion, if we knew how fast the peak moves, then that would give us the complete kind of growth rate. It turns out that the linear part's velocity and the peak velocity is identical. And this part I just said is analytically tractable. It's just the slope of the seed exponent. So using our conservation law, we also know the growth rate. So this is a little example. If you have an initial condition like this is the seed's initial shape, just a Gaussian, and then, did I say? So this exponent is just minus zeta squared, which I'll denote as h zeta, and then the slope is proportional to, well, I think I skipped too many steps, but it turns out that the slope of this is equal to, in the linear regime, always proportional to the propagation distance. And so derivative of zeta is just the zeta squared is zeta. So um, did I make a mistake here? I think the laws are correct, but I think I must have skipped a step here. But basically, using this kind of linear part, you can tell how fast the velocity of this leading front moves. And as a result, you know how fast the peak moves. So you can just use the estimate I gave before. The peak motion times the amplitude equals a naught square root constant. And from that, you can say that the front amplitude also grows as square root of tau. And this is what exactly kind of my 1D, 1D, yeah, 1D, I don't want to call it a simulation. Yeah, 1D code told. So growth rate is indeed proportional to the square root of propagation distance, and the front moves inversely proportional to uh, 1 over square root of tau. So this is just an example for Gaussian pulses, but using this kind of same logic, you can do this with Gaussian pulses equals triangular pulse. So peak moves as square root of tau, and the peak amplitude also grows as square root of tau. So the peak and the kind of motion is proportional to each other. So that's why you have a b. Well, there's also a typo here, b squared proportional to zeta. And then if you have an nth power super Gaussian seed, then you also have a similar relationship. So eighth order super Gaussian seed will lead to a seventh power polynomial kind of seed pulse growth. And if you have an exponential seed, actually it wouldn't grow. It would just give you a flat top pulse profile. And then I briefly mentioned that lasers required to drive these nuclear fuel have complicated shapes. So can I make something like this? So I can use a piecewise seed and it will grow to a different kind of level plateaus. You can use a low foot or a high foot. So indeed, using a piecewise seed lets us get piecewise plateaus. So it seems like by specifying a particular seed shape, we should be able to kind of convert the seed into a particular final shape with given uh, desired intensity and duration profile. Actually, that's most of what I have for this, but just for like a future directions, we, I don't know if anyone noticed, but this term disappeared magically. And this is good approximation when the damping is very strong, which is typically where all these um, exmer like uh, stimulate Brillouin scattering experiments operate on. But at some point, this term will grow and it'll cause a ringing of the acoustic wave. So it's worth investigating that at some point. And then we didn't include phase mismatch. So this leads to more complex beat wave evolution, and we haven't addressed that either. And then we also didn't think about maybe the pumps can look more interesting, like a time-independent pump intensity. Then under some conditions, I'm a theorist, so I like pretty things, and self-similar solutions actually were one of the motivations about why we are trying to do. So I wonder if we can change some of these parameters, like I think Mazama was working on the gain parameters, so maybe it changes according to time, or if the pump intensity changes according to time, then the form of these equations will have different dependencies, and you may end up producing self-similar kind of pulse shapes in space and time. So that's another direction that I think we're interested in. And then when Gennady wrote the grant, I think we promised we'll do multi-dimensional effects and kinetic effects. We're working on that. So for example, the diffraction of the wave was totally neglected here. This is a 1D model, and we need to maybe work on particle models to see if a lot of these hydro models indeed make sense, or we really need physical particles, because kinetics is actually traditionally where our group comes from. Uh, And here's my summary, and I'll take any questions.
Thank you, Jihoon. That was an excellent talk. Um, I have a question if no one else has
Yep.
one right now. Um, so, earlier you were talking about energy conversions for fusion, all these different ways. What would be the energy conversion for like temporally compressing a pulse? Like, how efficient is this process?
So when you're in the linear regime, well, let me just try to find it. So when your pulse amplitude is too low, like everything is here, then you actually have a horrible conversion efficiency. But when your pulse evolves to this kind of nonlinear part, you can see that the pump is completely eaten by the seed. So it actually depends on how fast your seed grows to the level that it completely eats the pulse. I think there might be a simple relation to that, at least in the 1D limit. We did some preliminary investigations, but we don't have a complete answer. It might actually depend a little bit on the details of the initial C shape, but we're still working on it.
Okay, thank you.
Hi,
Yeah,
can I ask a question to
yeah,
you?
yeah.
Oh, okay. Thank you. Thank you. Very nice presentation. I have a question regarding that is in the same uh, figure which was showing that. No, no,
Yes.
yes. Here, does this the non-linearity part makes a soliton here?
Yeah, I think this is somewhat solid. Yeah, like a lot of the literature I've been referring to is like it's very close to this, but if you look at the equations, actually, the solitonic ones have a usually. So these equations are not new. This is a very simple equation. It's
Yeah.
a two-wave equation, which is well known. People, I don't like. I'm not from a solitonic background, but usually when people study soliton, there's an extra time or zeta term here. Yeah.
Okay.
I don't actually don't even know like what you can. It's a propagating structure, so it looks like a soliton, but it doesn't have a constant velocity. So is it really a soliton? I'm not sure.
Okay. That's okay.
Yeah.
That's the question from that the last slide which was showing that
This one? Wait.
the next the last
Ah,
slide of your presentation before conclusion. Yes.
here?
Yeah. The point was that if you remember, we were discussing that. Did you think about that? How could we relate these equations to the gain? Do you know?
I think the gain term is living here and here, but if it becomes a dynamic variable, then so see gain like a time-dependent gas density or time-dependent gain or some I don't know like it really because this is a model and if you put in something that makes physical sense, it'll do different things, right?
Yeah, yeah, yeah. I
Like
understand that point. Yeah.
yeah, like when I initially began this, Gennady really wanted me to do self-similar solutions, and I found out that you get self-similar solutions only if you feed some particular functional dependencies. I don't know if these were real or not, but if you find what kind of time or zeta or like moving frame dependencies the gain can have, then we must be able to construct these self-similar solutions and maybe observe them.
Mm. Okay, thank you.
Yeah, thank you.
Well, that was kind
Um,
of, go ahead, whoever was going to interrupt.
yeah, this is AJ, and by the Jihoon, wonderful, wonderful
Thank
talk.
you.
So I have like a really simple question. For the seed, you took three cases. You took Gaussian, super Gaussian, and exponential.
Yeah,
So this is the pulse we are talking about, right?
yeah.
So what do you mean by exponential? You're talking about the front of the pulse,
Mm.
or like what does it physically mean?
Oh, it just means like imagine you have some seed shape, right? You can always write some function as exponential of something, right?
So um, so you're talking about the exponential decay or something there, right?
Doesn't have to be decay. You can have a polynomial and then the h would be logarithm, right?
Just like Gaussian or anything, you are in this
It
case,
doesn't
then,
have
right?
to be Gaussian. We actually the shape of h determines everything, at least in the two-way limit.
Mhm, mhm.
Yeah, it's really weird. I do I have other examples? I have more recent ones, but I don't have a, let me just, no, sorry, I don't think I put it in the backup slide.
No, you're good. Yeah, let me think about it too. Yeah.
Oh, like, or you mean this one?
In this case, yeah, like why do you have like three cases? Like,
Oh, we just wanted to see how a seed initial shape leads to something. So my understanding of this problem is Connor from Exeter
hmm?
has a seed generating machine. It may be Gaussian, it may be super Gaussian, it may be exponential, it may be polynomial. So if Connor makes something, what my motivation was if Connor can produce something, how would it evolve?
Okay, this is exactly the pulse shape, then intensity, right?
Yeah,
Okay,
yeah.
interesting, interesting. Thank
Yeah.
you. Mhm.
Yeah, thank you.
So, going into some of your like future works that you're planning on doing for the multidimensional effects, what exactly are you thinking about including for these?
Well, I haven't done too much, but diffraction I think is supposed to be included. I wrote it down, I just forgot the form definition. Yeah, basically diffraction, focusing, or actually I think that's it. Or what other multidimensional effects? Because we usually think of this in terms of vacuum, right?
Mhm.
Or gases. I guess. Hmm. Yeah, actually, yeah, I haven't worked on it too much, so I don't know actually.
Mhm.
Multi-dimensional effects, our group is actually more focused on like kinetic effects. So I'm from like a particles interacting with fields type of person. So Gennady's idea was to use like some Monte Carlo simulation to put like a population of particles and then they would interact with the gas. And hopefully we should be able to reproduce these. Yeah.
Yeah, that would be a really interesting way of looking at the problem. Usually you see the
Yeah.
waves instead of the particles, but they're exactly the same. I mean, it's
Yeah. Yeah.
so.
Yeah. Yeah.
uh, And that would be an interesting way of looking at, obviously, you have your gain terms showing in here, and we know the gain changes with pressure. So I'm
Yeah.
curious if the particle way
Mm.
would be easier to look at pressure effects.
Yeah.
Obviously, you need the gain effects, and it's that would be very, very complex to put it all into one code, but that would be very interesting to see.
Yeah, I like self-similar solutions. So if there's like a time-dependent gain, then yeah, maybe you can make it grow super fast. Like instead of doing I don't know, we probably don't want quite exponential, but like some weird, yeah, I don't know. It's just very fascinating for me. Yeah.
Yeah, it would be very interesting. Well, are there any other questions from anyone? You can ask something simple, complicated, it doesn't matter.
I have a question for you.
Mhm,
Could it be possible for you or the guy, I forgot the name of your group, who has done the work on Everbach results who was Stephen, right?
mhm. Yeah,
Yeah,
Stephen. Yeah.
Stephen, yeah. Could it be possible for you to share or give that presentation, because it would be easy for us to compare what we are doing, and then we can may think about that, what the limit precautions we have, or what type of systems we need to use to
Mhm.
enhance or to analyze or directly match the results with the experimentalists.
Yeah, I could definitely talk with him and see if he's available. And this kind of brings up the next thing I was going to mention. He will be at IFE-STAR. I don't know if you are attending the conference or
I
not.
don't think so.
Um, but we can try to set up a meeting with your PI or something. I make no promises, of course, but we will be canceling next month's meeting because of IFE-STAR. It overlaps with it, so we will pick them up again starting in May. So
And it,
just to give that heads up. And anyone coming to IFE-STAR, we are working on trying to plan some student events. So we will contact everyone later about that. But yeah, I'll talk with them and see.
okay.
Are there any other questions from anyone? Well, if not, I want to say thank you again to Jihoon for giving an excellent talk. This was very interesting, and I definitely learned a lot, and I hope others did as well. So have a great rest of your day, and I will work on sending out this video to everyone.
Thank you.
See you
Thank
guys.
you.
Thank you so much.
Thank
You
you.